Kia ora koutou, ngā mihi nui. It's a real pleasure to be asked to talk with you all. It's a slightly weird environment. It's not like an open theatre where you see the reaction of people to stuff, so it feels a little weird. Those of you that, I'm sure lots of you tried teaching during lockdown using Zoom, and I actually found that quite pleasurable because it was very interactive. I used to have sort of 2 students at a time, but having you all scribble on the screen, all 160 of you, could be a little troublesome. So I'm going to pursue the issue of we'll use the terms conceptual understanding and procedural fluency. And you can see from the title that I'm already saying that I think a balance between those two things is really important. You can see in the pictures there, we've got, this is scenes from a whole class lesson we took at a school in Melbourne. And I think from memory, the problem is that there are 4 people and they're sharing 3 jars of jelly beans, and we probably need to be careful about food now, but and there are 36 jelly beans in each jar, and you know, how many, if there's equal shares, how many should each of the 4 people get? And you can see from the right-hand side that there is, we're expecting a degree of procedural fluency, aren't we? We're thinking that, we're hoping that the students are going to behave multiplicatively towards that problem. But at the same time, there's a lovely opportunity to think about the concept of equal sharing and fractions in particular, ratios, if you like. So in that same lesson, we've got both of those things going on. So here are my aims anyway. We were supposed to say those. So I'm going to try and give you some background about research literature and bring some recent research literature into the story. And what the literature is actually suggesting about the connection between conceptual understanding and teaching procedures. And I'll try and define what I mean by those 2 terms a wee bit later. And I'm going to try and provide some examples of that what I consider the 2-way relationship between the between concepts and procedures. And I've tried to capture scenarios which range right across, because I'm aware that we have people ranging from early primary through to secondary school. So we're going to see a bit of both. You're going to see a couple of examples from my work with secondary students at the moment. Okay, this is a dot back in time. I think it's appropriate we stand on the shoulders of giants, as Isaac Newton used to say. So this is 1976. Actually, Skemp wrote before that. I still have, I'll hold it up for you. Those of you that think I pinched this from the Palmerston North Teachers College Library, you'd be quite correct. No, I didn't pinch it. They were throwing it out, so I grabbed it. 1973, Skemp wrote about this. And he, in the paper in 1976, and it's easily accessible online, he talked about 2 different ways in which the word understanding is actually used. And he even went so far as to say that he felt that there were 2 different subjects being taught. And he made the distinction between what he called relational understanding, that's knowing what to do and why you might be doing it. So if you like, it's transfer of understanding and procedures. And he contrasted that with instrumental understanding. That's the knowing rules, but really not knowing why the rules work, and certainly not having a sense of when you apply them. I don't think Skemp was saying that procedures are unimportant. He was saying that it's important to know why they work and when to use them. So he was making a distinction from what he observed, that a lot of students were just being taught rules without any sort of sense of why the rules worked, or why you might be using them, or when you might be using them. Now, if we go forward just a few years, it's interesting that you think of time frames, don't you? 1976, gosh, that's a long time ago. 2001, a bit more recent. Now that's 9 years after our 92 curriculum came out. And this is a lovely diagram of the mathematical proficiencies as the National Research Council report suggested, Jeremy Kilpatrick and his team. And that image of the knotted rope looks pretty familiar to us who were around in 92 when the 92 curriculum was being developed, because we had mathematical process strands. Now, not all of those are conserved in this diagram. Those of you that remember will see, okay, well, you see strategic competence, you might think problem solving, and adaptive reasoning, or we had logic and reasoning. But two I want to highlight that came out in 2001. This report's been reasonably influential in the United States. Very influential in Australia, actually, because 4 of those proficiencies underpin their curriculum development, which has been relatively recent. Conceptual understanding, and you can see that connected nature that Skemp was talking about, can't you? Integrated and functional, which means you can actually put them to use, the concepts. And you also see this notion of procedural fluency. Now, that doesn't sound that radical, but in the United States at that time it was, that someone will be saying, actually, you need to know how to do things. But notice also that there's a measure of understanding and flexibility involved in that. So the word flexibility is used alongside procedures. So it's not just, you just know how to do something, but you can actually operate flexibly about when you choose to use it, and you're accurate and efficient means you don't spend too much work doing it. So already in 2001, we have a kind of almost a rebalancing, and it had some impact in the States, probably not as much as it should have. Okay, let's define what we mean by a concept. Now I'm going to borrow a little bit of an idea from one of my favorite theorists called Andrea de Souza, and he works in UCLA. And this idea is not just his, there are other people who've worked on it. So here's Isaac Newton, he's sitting under the apple tree. You all know the story. Evidently it's a load of baloney. He got sick of people asking him how he came up with gravity, and so he made up this story about, you know, apples falling on his head and stuff, because it seemed to keep people quiet. But let's distinguish 2 things. When Isaac looks and sees that an apple falls, in fact, all things that fall loose fall towards the ground. That's something perceptive. So he sees that. And the term that de Souza would use is a percept. Now, Tall and Mike Thomas and people like that also use this term as well. But when you see something and you notice something happening, you're perceiving it. That's not the same as a concept. So when you invent a theory, you conceive of a way to explain and to model what's happening. So concepts are not directly observable, they're imposed by people on what they see. So if you like, a concept is, you have to create it and it's abstract, and hopefully it's transferable across a whole bunch of situations. So there's a difference between just seeing something and generalizing and actually coming up with a, if you like, a theory, an idea to explain it and to model it. So that's what a concept is. It's something that goes on in your head. And we forget that often because it seems obvious to us that students should see, for instance, a concept as simple as a triangle when they walk around, but you have to impose that idea of a triangle on what you see. A procedure is a performance, it's performance of a sequence of actions. So, for instance, this person here might have a sequence of actions that they know will produce a very nice kitchen table that you can use. So that's what we mean by a procedure. Now it's synonymous with the word algorithm. Well, it's become that way. Algorithm initially had a much more specific meaning, but so when you see the word algorithm in computational thinking, that's what it means. It's a set of procedures that you know are going to give you some kind of outcome. So it's goal-driven in the sense that you're trying to achieve something. And because when we talk in maths education about algorithms, we're frequently just referring to, say, written forms of calculation. Algorithm, the meaning of algorithm is much broader than that. Okay, now in maths we have lots of concepts, so let's throw a few around. Now, cardinality. Now, if you're working with junior students, that's a really important idea. So my colleague Anne Gervasoni describes this as the meniness of a set, which is a very nice kind of idea. I'm not sure, it's not a tautology, but it's understanding that a count actually tells you something about the number of things in a set. And we have that procedure that's really important that goes alongside that, and that's actually being able to count forwards and backwards, name the number after, all that sort of thing. So there's a whole bunch of procedures associated with understanding cardinality. And you kind of can't have one without the other meaningfully. If you're going to count with meaning, you need to understand cardinality. We have concepts like reflective symmetry, which might have to do with the idea of you know, when an object actually has reflective symmetry, i.e. whether, you know, a mirror can be positioned and you look at the object and it looks the same, even though you can only really see half of it. And the procedure of being able to locate lines of symmetry. Actually do that effectively, you need to know something about the concept. Unit of measure, we could spend a whole 45 minutes talking about measurement and the attributes of units of measure, that part of the attribute that you're measuring. They fit together with no gaps and overlaps, all that sort of stuff. Alongside that, at the end of the day, we want students to be able to actually measure things like capacity. That's one attribute. So there's a procedure of being able to measure, but there's a concept of unit of measure and where those units are on a scale, for example. Those things fit together. And it gets, as we ramp up, there are lots more complicated. The part-whole relationship, multiplicative part-whole relationship is a proportion, and we need to kick that concept in when we're calculating equivalent fractions, if we're going to do that with any kind of meaning. And if we're in statistics, we have concepts like distribution, and we might want to describe, we might want to use measures of center and spread to compare distributions of different groups, for example. When we're getting into secondary mathematics, I'd like to argue it happens before then, but we have the concept of a function, and one of the procedures might be to be able to graph functions. Okay, let's take an example more specifically, the concept of place value. Now, place value is a many splendid thing. Those of you that went to my AMA session on place value, where we scratched the surface of it, realize it's got lots of layers, that concept. I'm just going to show you a little snippet of one unit that belongs in a whole series. Now, if you were to do a search for level 2 place value on NZ Maths, you will find a whole suite of units around teaching place value. Very important idea. The unit actually starts off like this. This is me working with Jackie's class, I think, in Melbourne. And you can see that the students have all got a hundreds board picture. It actually goes to 110, I think. And basically, I'm just making a physical quantity with bundles of 10 and individual beans in there, just moving their counter to show how many are there. Now, what I'm trying to find out there is how much they understand about the structure of 2-digit numbers. If you go very quickly further on in the unit, you find things like this, which is the idea of using a calculator change situation. So can the students change 78? I can't see it, it's behind people's heads, 38 I think. Can they change 78 into 38 with one single operation on the calculator? So you can see already in that unit, we've got an idea, we're developing this concept of place value. That's the way it's structured. The understanding that 10 of one unit makes the next unit and so forth. And at the same time, we are involving calculation. I think there must be a whole lot of kids around New Zealand that wonder why they're studying place value if we don't put it to work. So if that's all we do, we model structuring 10s and 1s, etc., but we don't actually involve calculation. I'm sure there's a lot of year 2 and 3 kids are wondering why on earth we're studying this thing called place value. I suppose somebody will tell me how it's useful. You get into calculation and they see why it's useful. Okay, now this relationship between concepts and procedures becomes a little more obvious and a clearer focus of attention when you start trying to ask yourself questions about your own teaching. So here's one. I'd like you to have a think about this. always, it is a statement where you can decide where you are on the Likert scale down below. So always begin instruction about a topic with the introduction of the key concepts. So if you were to start with place value, you would do something about the structure of, tens and ones or whatever size numbers the kids are working with. So how would you feel about that? Where would you locate yourself on that Likert scale? Would your response vary depending on the topic? Maybe. Let's try something else. Where would you sit on this? Students need to learn procedures first and the understanding comes later. Well, I've heard lots of people say that to me. Do you believe it? Would you strongly disagree with that? Or would you agree? Strongly agree. Where do you sit on that one? Does it depend on the topic you're dealing with? Would you change your mind if it was a different topic? Now, pursuing the idea of topics. Some concepts like division of fractions, congratulations if you tried to teach that, are just too hard for students to really understand. So you just teach them how to do it in those kinds of situations. Now, if you've ever tried to teach division of fractions with understanding, you'll realize that the understanding is really complex. It's a very complex relationship between the units, the unit that's you're measuring with and the unit that it's measured into. So where do you sit on that? So you begin to realize when you ask yourself questions about how you go about teaching, that yes, I teach concepts first, then procedures, or the other way around becomes a little bit put under question. You start asking yourself really important questions about how you do actually teach. So I like to think that I do both, I think. So here's a class, I think the year 7 students, so they would be about 12 here in Melbourne, and we're looking at the idea of magic squares. So you might say, oh, well, that's just simply about calculation. Well, in that same lesson, it's more than that. So we start off with the idea of, could you actually use those digits and create a magic square where the sum of the diagonals and the columns and the rows is all the same? And the kids are playing around with that and trying to figure out where they put numbers. And here's this, you notice we've used sort of tau models, just unifix cube models to kind of put taus where they think the numbers are. And he's trying to explain why it works. So it's getting much more deeply into a concept of, it's kind of an averaging concept really about balance. And also, he's trying to say, well, look, if you kind of move these around, they'd kind of all flatten out and they would be the same as these if you move them around. And then the challenge for the students is, okay, well, you've got one example there. Can you create some others? What can you actually do with that one example? What can you do to the numbers in that one example so that it still stays magic? Can you multiply the numbers by the same amount? Can you add and subtract the same amount from them and it's still magic? What happens if you square them, for example, multiply them by themselves? Does it still stay magic? So we're moving beyond just the idea of carrying out a procedure and doing some calculation to actually teasing out some really interesting concepts about variance and invariance, what you can change and what you can't change in the situation. And it's always lovely when people are trying to explain how they know what they think they know. You can see various expressions, can't you, as you sort of wander around. So I like to think in that lesson, yes, there's a bunch of procedure going on. They are adding, multiplying, etc. numbers, but they're also thinking really hard about some pretty key key ideas, concepts in mathematics, like variance and invariance. Okay, so I'm kind of building up a little bit of a case here, and we're going to try and play this and see how the sound goes. So you're already getting the idea that I'm coming from a perspective that I think they're both important. Now, let me give you another reason why I think they're both important. Let's see if we can get, this is Jenny. Now, Jenny is just about 6 when she's interviewed in this video. And it looks like
Here's a packet of tennis balls. How many balls would there be in 4 packets? Do you want to put your fingers up so I can see what you're doing there? Tell me how you worked that out.
Because I put up, I counted 3 each time until I counted 4 sets of 3, and then I worked it out like that. And
could you do that a faster way without counting them one by one?
You could count by 3s.
Could you? Can you do that for me?
3. Damn, I didn't know how to count by 3s.
You haven't learned about counting by 3s yet. Sure. Here's a packet of tennis balls.
That on. We want to get past it. Okay, I just think that's a lovely piece of video. By the way, Jenny was the daughter of one of the research assistants at the university I work for in Melbourne, and she's now well into her 20s, and I think just got married actually. So that's an old video, but it's really interesting to see that she has a preferred strategy, which is basically to count in ones. But she actually has a concept for something more sophisticated. She understands that she could treat those 3s as units, and she could use the procedure of skip counting. The only problem she's got is that she doesn't actually have the knowledge to enact that procedure. So one of the things we need to think about with procedures is to stop regarding them as absolutely, mastered is a nice way to put it, because we know that concepts are kind of ever evolving. Procedures are as well. You can get thrown out by a problem that you don't have the knowledge to enact, even though there's a procedure that will be more efficient than the one you use. So let's just think about procedures as kind of evolving as well, and then we don't get stuck in this idea that a procedure is always going to be able to carry that out exactly. You just develop more sophistication. If you look at the research, you can think about early this situation with tennis balls, as what is it, 4 groups of 3, 4 times 3. And you could say, oh, okay, in sort of developmental theory, a lot of the trajectories would say, oh, okay, so she's using a counting-based strategy involving ones. However, she actually knows that she could do this. Skip counting is a kind of form of additive build-up, just like 3 plus 3 is 6, etc. So she already knows that she could do that, just hasn't got the knowledge to enact it in this situation. If the tennis balls were in packets of 2, she might have had. And she's a wee way off actually deriving, so using multiplication facts that she knows to get new facts. But that's, if you look at the trajectories of early multiplicative thinking, that's what many of the growth paths tell you it looks like. My favorite and more recent piece of research about the growth of early multiplicative thinking is Sheeran and Fewson's. And they're basically saying, hang on a minute, it's not that clear cut. What happens is that students gradually get more sophisticated as they go, on the basis of the more knowledge they get, the more they understand, the greater, the more efficient those procedures become. So they're saying that an individual student like Jenny might be able to use this kind of strategy on one problem and a different strategy on another one. So you just need to be a bit mindful that procedures are not an exact science. It's not like mastery. You're getting more and more competent, if you like, at carrying out a procedure. Okay, let's go really forward in time. This is actually, they've just published, these folks have just published a book chapter in 2019, I think it is, saying much the same kind of thing. So this is Bethany Riddle Johnson, who's sort of, I won't describe her as an emerging giant in maths education, that would be unfair, but she's one of that very powerful school in Vanderbilt University, and she's basically a maths educational psychologist, really. Let's have a look at what that group of authors have got to say about procedural and conceptual knowledge. They say there's no clear, there is clear evidence for the bidirectional relationship. In other words, procedures support understanding, conceptual understanding, and conceptual understanding supports the development of efficient and accurate procedures. So it's a myth to say that just because you're being taught a procedure, that's not going to support your growth of concepts. And she's saying the team is saying that we don't really know about the advantages of particular order. So whether it's better to teach concepts first and procedures later, or the other way around, or maybe you mix them all up. And she's saying basically that this may be a result of a kind of hegemony. A hegemony is kind of like an idea that's all pervasive. It's almost like everybody agrees with it, so it's not tested. And that group is certainly saying that about the reform culture in the United States, which is strongly saying, teach conceptual understanding first before you get into any kind of procedures. And they're questioning that. They're strongly suggesting this idea, and I'm in favour of it too, to be honest, that you need to balance conceptual focused learning opportunities, and that might be direct instruction. In Japan, they have lesson types called the conceptual lesson, where the teacher does actually put concepts in harm's way for the kids. So that's quite a direct way of conveying mathematical ideas to kids. And of course, they support that by applications which take the form of investigations and problem solving. We sort of have this illusion of Asian classrooms as just being practice-based. It's not. I've got a set of Japanese textbooks on my bookshelf here. I can assure you it's not just practice-based. And at the same time, we need to also have opportunities to learn that are based on learning procedures. And they might be direct instruction. Those of us who are old enough will remember actually trying to support students to learn how to do long division with the help of material. I can still remember Belinda Mons. I hope she's not listening. She was in my class in Fielding, year 5 class, we would call them now. After the 3rd lesson, midway through, place value blocks everywhere. We're trying to work out what's actually going on when you do long division. Belinda says, "Oh, I've got it now. Can I leave?" And I said, "Yeah, that's fine, away you go." And she did. And I still to this day have no idea how she managed to do that, but somehow or another it had all kind of come together for her, the concept of place value and the procedure. So basically they're saying that we need to do both of those things. It's not either or, and it's not one before the other, and they're strongly in favour of this metaphor of bootstrapping, which is bouncing between the two of them. So you may start off with a concept idea, and then you support it with procedure. Excuse me. And so you might start the other way around with a procedure. You might start with that calculator activity of the change game. Oh, okay, we found that a bit tricky. Maybe we can learn something about the concept of place value of 10s and 1s, that it makes it a bit easier to play that game. And so they're suggesting that you can bounce between those two things, rather than see them as opposing camps. Okay. Now let's talk about some situations and try and bring this to life a little bit by some examples. So here's dad teaching son. In fact, this was on. We were talking about national television, which we've been writing stuff for, and this was actually modelled on national television. So, okay, the student's got the problem of working out 9 plus 5. It might just be in an equation, it might be a story, I don't know. And here's dad saying the easy way to add 9 plus 5 is to hold the 9 in your head and then count on 10, 11, 12, 13, 14. I suspect the kid is like my daughter was, my daughter Kylie, when she was year 3. What does he know? He may be a lecturer in maths education at Massey University, but he's my dad, he's not a teacher. But what's the aim of the adult in this case? It's clearly about procedure. It's clearly about just getting an answer. It's what Skemp would say is rules without reasons. Now, if that's the way we teach counting on, then we are doing kids a disservice, I feel, because what should underpin counting on as a strategy is an understanding of cardinality. So, oh goodness, 1978, dare we stand on the shoulders of some other giants? Okay, early number, Rochelle Gelman's work was absolutely stunning. So she came up, well, not by herself, but she came up with 5 principles of counting, which we often forget. Now, to me, the most important one is this one. It's the idea of cardinality. So assuming you count 1 to 1, and you count in a stable order, you don't miss numbers out, then when you count a collection, the last number tells you how many are in the whole collection. That seems like a really obvious idea. If it was obvious, kids would not need to be told to count on, they'd work it out for themselves.
Count out 7 counters.
Okay, sorry.
Use different colors.
Voice. Okay. So
put your counters onto the strip, one at a time like this. Start with the blue counters. When you finish, what number will the last counter go on?
Now that, here's another story. Rural school outside of Invercargill, I forget the name of it. But we had a class of 5 and 6-year-olds, and we started like this. Can you get 7 counters? And mix up the colours a little bit. If you put them on the strip, and where would the last one come to? And you could see half of the students going, well, that's a really dumb question. Why would you ask me that? And the other half going, oh, okay, gee, I wonder what would actually happen. So we've found actually number strip is a really powerful representation of cardinality. Incidentally, we then asked them, oh, okay, so the last one came to 7 years, you all agreed on that. Okay, what would happen if you started with the yellow one first? That caused consternation for several kids. The other kids were looking at us going, don't be so silly, it's still going to be 7. Now, it seems to me that when you do those kind of things with students and then you ask them, oh, here, open it, give me your hand. I'm going to give you 2 more. How many will you have then? It seems the most obvious thing in the world that you would understand the 7 has told you about all of those, that set of counters, and that you're going to go 8, 9 to work out how many there are there. And that's what we've found, that when we put those kind of experience in front of kids, they just invent counting on, because they're dealing explicitly with cardinality, that last, that 7 represents the whole lot. It's not the same if you put one counter on 7, for obvious reasons, because the other 6 aren't there. So we've done lots of messing around with number strips. We've done things like this. Maybe we haven't done anything.
How many red counters are there? What is wrong? Why is 12 not right?
So we throw curveballs at kids like this.
That is better. Now you know how many red counters are there.
So that only works if you've actually maintained that 1-to-1 principle in a stable order. If you leave things out, the last number doesn't tell you how many. So I'm going to skim through a little bit of this. You get the idea, though. We're actually developing those principles of counting. So alongside the procedure of being able to count, we're developing the concept of cardinality with students, which is, if in theory, is the reason that you would count on as a strategy. You're not being told that you hold the number in your head and count on. You've worked that out for yourself. And I'm going to go skim me past that.
How many dogs are there? How many bones are there? Is there a bone for each dog?
And then, of course, we could do that. Now, I always used to contrast the 5-year-olds I taught. My first year teaching was 5-year-old students, actually. And there were students that would just say to you, well, yeah, there's 8 dogs and there's 8 bones. Yeah, that's fine. And there'd be other students who weren't convinced until they actually did that one-to-one matching. If you understand cardinality, then models like this make sense to you. In fact, this is a nice way of understanding that you can apply cardinality. So if you have a difference between the number of dogs and the number of bones, and you actually model that with counters in the strip below, you actually model the idea of how you would find out the difference between 5 and 6. Now, that's a really simple example, but lining up 2 number strips like that is a very powerful representation of how to find difference. So that's a junior example about, oh, okay, have we got procedure in there? Yes, we are interested in counting things. Are we interested in concept? Yes, we're very interested in the concept of cardinality. Are we interested in a procedure to find the difference between 2 numbers? Yes, we are. That's underpinned by the concept of a difference in cardinality between 2 sets. So that, if you like, they're bootstrapping off one another. And in the same lesson, we will be doing that. Now, I apologize if you're teaching 5-year-olds, but my tutoring work at the moment, I do some classes with secondary students. Now, this is Holly. It's not really Holly, but she's at level 1 NCA. So let's really ramp up the gears. So she's 15 years old. She's trying to get some credits, as most 15-year-olds are. And at the moment, she's working on a standard to do with linear equations. Well, it's other equations as well, but that'll do. So when you see that equation, Holly, well, tell me what that means. I'm not sure. It's hard to explain, really, which is kind of Holly's way of saying, I don't really know what that is representing. So she doesn't really have a concept of the equation as representing a relationship. So we talk about things like this. I said, okay, so I tell her explicitly what the concept's about. It's kind of like a recipe, a formula about 2 things that change. Well, it can be more than 2, but here it's 2 that change relative to one another. So we use the example, what happened to your height as you got older? And she says, oh, I got taller, blah, 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 blah. Oh, okay, so that's like a relationship, isn't it? As your age increased, so did your height. So we could think of your age as being kind of like X, and we could have different numbers for X and Y being like your height. And we used other examples like, you know, a shadow or something like that during the day, or examples where there was kind of covariation going on. So we're explicitly dealing with the concept of what that equation is representing. It's actually a way of representing a function. Okay. So things become really interesting then when we flick over to procedure. Now, this is a lovely graphing app that I use all the time. Desmos is just wonderful. It's so easy to use. So, okay, Holly, can you, you know, graph that equation? Now, I'm very conscious that with the software can mean that kids don't attend to particular things. They don't have to create the scale and all that sort of stuff. So very happily, the machine kind of tunes out the graph. Oh, what do you notice? Oh, it's a straight line. Why do you think that happens? Oh, I haven't really got any idea why that would happen. Okay, that's fine. A procedural question. Can you give me a point that lies on that graph? That's pretty basic, but I know from listening to Di Seaman's team in Australia, we take that for granted that students make that relationship between a line and the ordered pairs that lie along that line, let alone the location of those ordered pairs. Can you give me a point that lies on the graph? Holly, I keep forgetting which one is X and which one is Y. Okay, so I say, oh, well, I tell you, okay, X is the horizontal across and Y is the vertical up and down. Okay, so this is what we do because we're not sure about how to carry out that procedure. We literally write the equation and we rub out x and we put a value in there. Okay, so what do you think y will be? So Holly is quite happy. She calculates that out. Oh, that's kind of interesting. So when x is 3, then y is going to be 11. Back to the procedure. Plonk 3, 11 as an ordered pair, and it puts it there. Did it work? Yes, it does. Okay, so what's going on here is her idea of the concept of a function, an equation as a representation of it, is being embellished by the action of trying to find ordered pairs that sit along that line. So there's and by the way, I mean, this is a real story. I'm not making that up. Now she's at level 1. Have I got other students that do this? She's not alone. I've got someone working at year 12. He's doing level 2 NCA. He's factoring quadratics, and I'm saying, okay, what does that tell you? Can you think of a value of x that would make this function y equal to 0? Oh, yeah, -3 would work. Would there be another value? Oh, no, hang on. X can only have one value. So you're running into all these conceptual issues all the time with students. Okay, so I'm conscious of time, and I could give you lots of examples. So let's just kind of sum up without going too crazy. We could talk about trigonometry, but we've run out of time. Okay, key ideas here. Okay. When your preparation for teaching, make sure that you unpack both the conceptual ideas and the procedural issues around that topic that you're going to be teaching. Anticipate what those issues are likely to be and how the concepts are going to interact with the procedures. So don't treat them as separate things. Think about the interaction between them. And use frequent bootstrapping between the concepts and the procedures in your opportunities to learn. So no fixed order, play with it yourself, and you will find that you might spend a lot of time teaching a procedure. Okay, if you do it with understanding, it's going to improve the concept. And that, in a nutshell, is the end.